Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to solve a simple DC circuit problem when you have an inductor involved. So what we're looking at here is we have an EMF or a voltage source here, a switch, a resistor, and an inductor. And what we're going to do here is we're going to write an equation, solve it, and sketch a graph of current against time from that equation. So imagine the switch is closed. When the switch is closed, we're going to have a clockwise current, clockwise based on the polarity of that voltage source. It's important to realize, though, that this is going to be a time-dependent current because we have a very reasonable inductive load in the circuit. Remember, inductance is resistance to changes in current. Now, as far as how we analyze it the same way we analyze all circuit problems. Kirchhoff's law. So, imagine starting here. And I'm going to go ahead and go clockwise around the loop and write an equation. In fact, I've already did that here. But as we move clockwise, we're going to plus E minus IR minus the voltage across the inductor equals 0. And the voltage across an inductor is L di dt. So here's the equation we get when we apply Kirchhoff's law to a single loop. It's a differential equation. It's got a derivative in it, but it's reasonably easy to solve. Let's see. How about we write this? Let's put this term over here. How about L di dt is going to equal E minus IR. Why don't we put the L on the other side as well? So di over dt is going to equal E over L minus IR over L. Now we can put the dt on the right and the E minus IR on the left. So we're going to have di over, in fact, I'm going to move the E minus IR over here, E minus IR, but I'm going to leave that 1 over L on the right and multiply by dt. So that's going to equal dt over L. Right? This is now solvable by integration. Time starting at 0 and going to some generic time t. Current started at 0, going to the current that goes with that time. Now, right-hand integral is no problem at all, t over L. Left-hand integral, I'm going to go ahead and do a little substitution here. I'm going to let u equal E minus IR. If I do that, du is equal to minus dr. I'm sorry, minus di. Sorry again, minus RDI. That's what it's equal to. Third time's a charm. All right. If I is equal to 0, then U is equal to just E, and I'm getting that from here. And then if I is the time-dependent current we're looking for, then U is E minus IR. So now we can rewrite this integral. Equals integral, okay, instead of 0 to I, now we're running it from E to E minus IR. Right? DI is equal to minus du over R from right here. And then E minus IR is equal to U. All right, so now let's see what we got here. This left-hand integral is no problem at all. Integral dt is t, so this left-hand integral is t over L equals right-hand integral. Keeping in mind that this minus 1 over R can come out in front, and I'm going to go ahead and just shift it to the left-hand side by multiplying by R over L. So this is going to be minus RT over L equals. Then we're going to have integral du over u, that's natural log of u, evaluated at these limits. So that's going to be natural log of E minus IR over E. Right? Undoing the logarithm. This means E like natural exponential number E, 2.7 something, to this power equals this thing. So we're going to have E minus IR over E equals E to the minus RT over L. And now it's just a matter of solving this for I. Let's see, we're going to want to put this over here. So we're going to have E minus IR is equal to the E, the voltage E, times E to the minus RT over L. And we can solve that for I. We're just about done. We move this to the right, this to the left, and factor. We end up with E over R times the quantity 1 minus E to the minus RT over L. There we go. We got it. All right. So here's the function I was looking for. Here's some important things about that function. Look at this minus RT over L. If I wanted to, I could put this R down here. That would read E to the minus T over, and then at the bottom we'd have L over R. L over R has to have units of seconds, and it does if you work them out. That's called the time constant for the circuit. As far as functionally, like graphing this, well, you'll notice that at t equals 0, e to the 0 is 1, so the current would be 0. So I'm going to do my first sketch here. It's an exponential type of shape, and you'll notice this right here. If we take the limit of this expression as t goes to infinity, now keep in mind that this minus sign effectively means this is 1 over e to the RT over L. As t goes to infinity, that term goes to 0, and the current is equal to e over r. So the long-term current's e over r, and it gets there according to this exponential type of shape. It's looking something like this. Now, again, I talked, in my video about inductance. The inductance is going to affect the, how fast the current gets to its maximum value. So let's just say that this first curve is at some middle inductance, some mid value. If I take that inductor out and I replace it with a very, very small inductance, then this curve would get to its peak really fast. So that's what the curve would look like if your inductance is really small. And if I take that inductor out and put a really, really big inductor in, or a really powerful inductor, I should say, then the curve might look something like this. This would be for L large. Okay. So the point of this video was 1, how to write a Kirchhoff's equation when an inductor is involved. 2, how to solve it. In this case, it's solvable by separation of variables. 3, understanding these curves, really important. Very small inductance means the circuit will get to its peak really fast. Most of the circuits we look at in DC circuit labs, we didn't put an actual inductor in there. So the only inductance they have is due to just the current loop, just the circuit itself. Typically, those inductances are very, very, very small. So when you close the switch, you can pretty well almost instantly read your current. However, if we actually put like an iron core in the circuit that's got a lot of these loops, hundreds of them, we put something like that in there, then the circuit's going to have a massive inductance. And now what will happen is the current versus time will get one of these shapes, something like this. We'll have to wait a little while to get the steady state current out of it. So anyway, I hope this video helped demonstrate how to solve circuit problems with inductors. Have a great day.